So I see you got the memo that it's Blue Shirt Day. It's how we roll here. We really want to have continuity. So we have a guest lecturer / helper today. This is Mr. Bergman. This is Mr. Mitras, like normal. And today we're going to be following up a little bit of what we talked about in the last video, which was calorimetry. And so in order to do that, we're going to try some examples. And this is where we have the fancy color pens here. And we're actually going to try these out.
So like hot stuff and cold stuff.
It's pretty much exactly that. I'm the green, you're the red.
Red. Why purple?
That's again, we can fix this in post-edit, because that's where we do all of our fixing, right?
yeah, right.
All right, so...
I don't believe that.
So if you take a look in your notes here, we are actually going to be dealing with how to figure out enthalpy when we're dealing with calorimetry. And so
there's 4 ways we can calculate enthalpy, and this is method number 1, for lack of a better term.
Yep.
And enthalpy, folks, right, that's where you're trying to find out the amount of energy in or the amount of energy out. So we have a problem here. Take a look at your notes. And we've got a chemical reaction. So if you got a chemical reaction, we got to write the balanced chemical reaction, right? So what do we got? Magnesium.
You don't have to say it that way, but it's so much more fun when you do, right?
Magnesium reacts with hydrochloric acid, which you know is HCl. And that forms what? Now, there might be clues in here. The initial temperature kilometers, the final temperature, I guess it doesn't
they give you no
that
clues.
to you.
But this is a single replacement reaction we've done in the past. So this is going to give us MgCl2.
MgCl2, because that's magnesium with the 2 charge, chloride with the minus, and then hydrogen is H2.
That's Brinkelhoff for
Mr.
those
Brinkelhoff.
Yeah.
That's right. So you got to keep Mr. Brinkelhoff. Balance this bad boy. You've got to put a 2 right here.
Okay.
Now, let's talk about this reaction. If you look at this reaction, he starts at 18.5 and he goes to 25.6. So the temperature's going up.
Correct.
So where would I put energy in this reaction?
That's a really good question.
Is it on the left side or the right side?
Well, is it increasing?
Well, the temperature's going up, so it looks like this is an interesting question. It depends on your system versus your surroundings.
We talked about that before, right?
It's leaving the system.
Correct.
Because it's heating up the air, or the container, actually. So the delta H is going to be on this side.
And what sign would that have?
And yeah, because that's on the right side of the equation, we're going to end up with a negative sign. Remember, energy can't be created or destroyed. Correct. There's no such thing as positive or negative energy, but the negative sign means energy's leaving the system, whereas the opposite, it's going into the system.
Remember the spoiled child that we talked about before? Yeah. If something's being done in the system, it's positive. If something's the system's doing it, it's negative. Yeah.
Now, to solve for delta H, if you recall, delta H, the units on delta H are kilojoules per moles.
Correct.
So I need to find the kilojoules, and then I need to find the moles. And I take the kilojoules, and I divide by the moles.
True story.
So that's it. So we're going to have 2 different ways we do both of them. With a balanced chemical equation, the moles is easy. We're going to use simple stoichiometry because we have 3.25 grams of this. Write down your knowns underneath your knowns. HCl, we have 125 milliliters of this.
But we're going to do a magic transition. Tell me why we can magically transform that.
What do you mean by magically transform?
Well, we say 125 milliliters. We have grams here. We cannot compare grams and milliliters, correct?
No,
so what do we do?
I think we have to make an assumption here as I look at this problem. We're going to make an assumption. I know this problem is that we're going to assume that the limiting reactant is the magnesium. We're not given the molarity of the HCl. We could, and it's possible that HCl would not be limiting. But let's make an assumption in this problem that the magnesium is limiting. So I'm going to convert. Do you have something else?
Yeah, I'm going to add. Actually, it's kind of interesting though. All of our solutions are in water, and water has a density of 1. So if we know that we have 125 milliliters, we could probably pretty safely make the assumption that it's 125-ish grams. And if you take a look at it, you have 3.25 grams of this and 125 grams of this. Now, this is the coefficients here are not gram ratios, they're mole ratios. Yeah. But if you take a look at the molar mass of this and the molar mass of this, it's going to be pretty obvious that the Mg is going to be our limiting reactant.
Yeah. So what I'm going to do is I'm going to convert grams of this into moles of H, which is weird, but that's what we're going to do, all right?
Okay.
So we're just going to get the moles. So I'm going to take 3.25 grams of Mg over 1. Now I want to convert grams to moles of magnesium. There's 24.3 grams of Mg in 1 mole of Mg. Now I just got that from the periodic table, all right? So just look it up on your periodic table if you don't know that. And then I'm going to say, now this right here is a 1. 1 mole of Mg is equal to 1 mole, if you will, of heat. All right, or in this gives this will get us our moles. So now I take my calculator, right? Get my calculator out, and I turn it on, and I take 3.25 divided by 24.3. That's it, right?
True story.
There's no other number, so we'll get 0.133. Yeah, it's
So 1.34?
0.13. Is it 4?
Yeah,
4
round up.
moles.
Yep.
So that's the number that's going to go here. All right, but that's not the only thing I want to do. I want to solve for the kilojoules. Now, to do the kilojoules from calorimetry, which we learned earlier in the previous video,
Want to use another color pen, or
equals
are you excited?
Q equals MC delta T. So we're going to use Q equals MCAT to solve this problem. Now, M is the mass of all of the chemicals together. So note here, we've got 125 grams, right, of the acid and 3.25 grams of the magnesium. So that would be 128 and a quarter. So this would be 128.25 grams times the specific heat of, now this is an interesting question. Well, we say, look, the heat capacity we're going to assume is 4.86.
Yeah, so what is water's heat capacity?
4.18.
4.18, and that's the standard for all water. This here is slightly higher, and it's a container that's keeping water and other stuff in it, so that makes sense.
So I write that up, 4.86 joules per gram degree Celsius. And delta T, what does the delta T stand for right here? That's the
final minus initial of temperature,
the
right?
change in temperature. It went from 25 or 18 to 25, so we take 25.6. 25.6 minus 18, we probably get this in our head. It's pretty simple math. 7.1.
I think our students are going to be using a calculator, so I'm glad you modeled that for them.
7.1 degrees Celsius. Notice, by the way, that when we look at this equation that the degrees Celsius cancels, the grams cancel, and bing. So now I'm going to take these three numbers, simply multiply them, right? So
While he's multiplying it silently, let me point out this to you here. Putting units in for the AP exam is incredibly important. They'll take off a point per problem if you don't show your units. And the nice thing about it is if you set up your units correctly, you'll end up with the unit you're looking for, which in this case happens to be joules.
So I end up with 4,425. Now notice that's joules.
Very important.
So that's joules, and usually in delta H's are reported in kilojoules per mole. So if you do the math, I'm not going to do too much detail. Divide by 1,000 because there's 1,000 joules in a kilojoule. That'd be 4.43 kilojoules. I'm going to round that. So if I'm trying to find the delta H, now I just plug this into my bad boy equation, right? I'm going to say 4.43 kilojoules, divide by my moles, which was this number here, 0.134 moles, and that equals, so here, I'm going to just take my calculator, I'm going to divide the previous answer by 1,000, right? That gives me my 4 points, and then I can now divide that number by 0.134, and I get 33.0 kilojoules per mole. Now, folks, there's one more step. That's the one thing I have forgotten to do. Think. What do we talk about? Energy is going, it's leaving the system.
The sign is really important here,
So
isn't
sign matters. So it's going to be negative because, of course, it's a exothermic reaction. Energy's leaving the system because it's heating up and going bye-bye.
True story. Delightful. All right, let's try one more just while we have you here. It's free labor, so why not, right? There is something that you mentioned a little bit earlier, that heat or energy is always conserved, right? So if I lose energy, it has to be picked up somewhere else. It's the cold hand on the back of the neck principle we talked about before, right? Heat's going to be transferred from your neck to your hand. You don't really transfer cold, right? So we're going to do a problem right now where we show how heat is being lost from something and gained by something else. And you should be aware, whatever heat is lost has to be gained by something else, correct?
All right, so let's kind of picture this one. You take a look, you've got your paper right here. We've got a container probably, and we've got a piece of copper, and we're heating it up to, it's a little cylinder, so draw a little cylinder, and it's heated up
I feel like I'm part
to
of the problem.
95.4 degrees Celsius. All right? Actually, when I first designed this problem, as a side note, I would boil water, and it would boil at 95.4 degrees Celsius. You might ask, wait a second, I thought it boiled at 100 degrees. But I was living in Colorado at the time, where the boiling point was actually about 95.4 degrees.
That is really funny.
So my students knew that as a matter of course. So we're heating this up to 95.4. We know that he has a mass of 46.2 grams. And then we're going to drop it into a bucket of water, right? So we get a bucket of water. We're going to take this bad boy, drop him into some water, and the water is initially at 19.6 degrees and 75 grams of it. And then, go ahead.
Can I just jump in here so real quick? The reason you put in the water here was just to get it up to that temperature. You could easily just have shown you the piece of metal up here
That's
with a
true.
particular temperature and throwing it into here. This water is not this water over here.
Yeah, what I did is I put it on top of a hot plate, and
you wanted to make
the
it that
boiling. I
temperature.
wanted to reheat it up to 95, or to
Clear.
the highest temperature I could get, which was 95 degrees. Now, and then the new temperature, so it goes from 19 and it goes to 21.8 degrees. Now, this is this whole idea that energy in equals energy out. So the energy that the copper loses
Has to be picked up by.
has to be picked by the energy of the water gaining. So this is actually what we would call, Q, if you will, equals Q.
Which is delightful in all steam, but we sometimes just to remind ourselves that something's being lost and gained, we use a little subscript. So
Yeah.
I don't know if you've done it before like that, but
Yeah, so
either
Q of the copper
Yep.
and Q of the water. All right, so MC delta T. So this would be the M of the copper.
Correct.
So the mass of the copper, I'm going to bring that bad boy down 46.2 grams times the specific heat of the copper.
which you have to have, or this problem is a no-go.
Calculate the heat capacity of the copper. Do you see, that's actually, we should have probably said that earlier. This is the question we're trying to find.
Yeah, we probably should have read the question fully before we
C
started.
copper. I knew that's what we were headed, but I forgot to mention it.
Yeah.
So C of copper, that's our X, if you will.
True.
Times the change in temperature of the copper. Now, this can get a little tricky. I find students have a struggle
Oh,
with this.
because of the sign.
Because it's 95.4 degrees initially. What temperature does the copper go to? What is his final temperature?
Well, you have to find the final temperature, right? Because if you have something cold and something hot, they're going to meet in the middle for their temperature
So
change.
his final temperature, a lot of people don't really see this, but the final temperature is 21.8 for both the copper and the water.
That's true.
So we have to subtract these two, right? Getting used to this type of calculator. 95.4 minus 21.8 gives me an interesting number, 73. So I subtracted these, that's 73.6 degrees.
73.6.
So 73.6 degrees. And then we'll do the same thing for the water. Now we do know everything about the water, so we know the mass of the water, which was 75 grams. Specific heat of water, it's not maybe listed here, but we would know it from earlier before.
Yeah, and I'll make an emphasis of it. And if you remember in the previous videos, we did make an emphasis of it being 4.184, correct?
Oh, you
do you
said-
put the 4 in the end?
Never
Okay.
used it.
Okay.
But we can put it there. That's fine. You'd be more accurate than me. And the change in the temperature of the water. This is a little tricky again. He goes from 19 to 21, or I always do it just to make everything positive. 21.8 minus 19.6. Yeah, 0.6.
Before we go, though, I want you to address how you're doing a positive value for both these, but if you looked at it, it would be a negative value. He's going to address the fact that this is actually a negative change in temperature at the end, because the positive Q
Yeah.
is equal to negative Q. But there's multiple ways of doing it.
I always just leave it positive.
I did too, and then I make the change at the end. But if you forget, you can end up ending your problem end up looking a little bit weird.
So I'm going to multiply the right side. 75 times 4.184 times 2.2 gives you 690.4. And then we're going to have a variable here, right? So I'm going to take 73.6 times 46.2, 3,400, times the C of the CU.
Now, just to be clear here, he's going to put a decimal on the end of that just because we want to make sure our significant figure
Yeah,
is.
that actually is exactly 3,400. So yeah, divide both sides by 3,400, right? 3,400s cancel. 690 divided by previous answer gives me C of the copper is equal to 0.203.
What units are we doing?
Now that's a
here?
good question. Let's think about that. What units do we have? Well, C's are in joules per gram degree Celsius. So that's the answer. Now that makes sense. Let's think about this for a moment. We talked about earlier, or you've talked about earlier, about the specific heat capacity of things. Water has a specific heat capacity
It's really high.
before, and it's like crazy high, and that's why living things happen, and it's lots of implications.
Important.
And this number here is a small number. Metals tend to have very small specific heat capacities. That's why you burn your feet when you walk on the concrete in the middle of the summer next to the swimming pool, because it has a low specific heat capacity. So that number makes a lot of sense.
So if we were to do a walkaway here, what are the two things that you think would probably be the most important walkways on solving these problems?
I think the biggest problem I see students make is right here, is figuring out the change in temperatures of the two. I mean, the big idea is, of course, that the energy in equals the energy out. That's sort of the big idea. And then you basically plug in the numbers. But the mistake I see students make is right here with this, the subtraction. Almost always with the metal, the water, they can see that difference, but they don't see that the final temperature of the thing you're dropping in the water is the same as the final temperature of the water.
Brilliant. Well, thank you so much for dropping in on us again, and thanks.
You guys are awesome.
All right, take care.
Take physics next year.
Always.